Hey everyone, these three lectures, 37A, 37B, and 37C, represent the end of our course on differential equations in linear algebra. It's pretty high-level stuff. I want you to get the basic idea of it, but really my main goal in talking about this content is to, I hope, inspire you to want to learn more about this content, and you can. You have the capability to do so. 37A is what this lecture is. You can see it's examples of nonlinear dynamics and analysis in 3 and more dimensions. Very broad overview with lots of pretty pictures and Mathematica usage. We'll talk about more on invariant spheres. We'll look at the same example from 36A. We'll also talk about how to think about it in spherical coordinates, which corresponds to the Mercator projection of the world map. The Lorenz System and Lorenz Attractor, which is exactly what you see right here. This is called the Lorenz Attractor. We're going to look at this system, and one very important aspect of it, it's chaotic. What does that mean? We want to get the basic idea of that. Something that's my personal favorite, I call it the Kinney Attractor. It's a system that I made for part of my thesis, and it's got an attractor, and I think it's kind of pretty as well, so I'm adding it into this lecture for fun. It doesn't have any applications as far as I know. It just is pretty interesting. We'll look at the two-body problem, which is when you've got two masses that are attracting each other under gravitation, although one of them is so big compared to the other, it's going to stay fixed at the origin. That simplifies things. And finally, we'll look at the double pendulum. Again, mostly with Mathematica to help us visualize things and understand things. We can't actually find formulas for solutions. All right, so let's start again by looking at that system with invariant spheres. I'm going to go pretty quickly through these slides. I showed these slides in lecture 36A. If you need to take the time to check these things, then you should pause the video and check as much as you can. Considering this particular 3D system, it is a nonlinear system. Where are the nonlinearities? The x times y, the y times z, the x squared, the x times z, and the x times y are our nonlinearities. This system is not a Hamiltonian system. It doesn't have the form of a Hamiltonian system. However, it does have a conserved quantity. This function, x squared plus y squared plus z squared, is conserved. What does that mean? Along solutions to this system, this quantity stays constant. In other words, since where this function is constant consists of spheres centered at the origin, look at its formula here, that means solutions have to stay on spheres centered at the origin. Along any solution curve, you can check that the derivative of this function along a solution curve where you assume x of t, y of t, z of t satisfy the differential equations, you can be found by the multivariable calculus chain rule to always equal 0. Notice this identically equal to 0 right here. That means it's true for all values of t. Now you don't see the t's in there explicitly, it's just in your mind. That is what proves that this quantity is conserved. That means solutions have to lie on spheres centered at the origin. And in the case when you've got invariant spheres, which is what these are called, you actually have to have an entire curve or curves of equilibrium points. It turns out that any vector field on a sphere, by the very nature of a sphere itself, has to have at least one equilibrium point. Okay, and in fact have two even. That's by the very nature of what's called the topology of the sphere. There's something called the Hairy Ball Theorem that you can look up to understand that, but it's a pretty high-level proof. In this case, we can solve the system of nonlinear algebra equations to find all the equilibrium points. There's infinitely many equilibrium points. And here are the details. You can check the algebra. Every point of this form is an equilibrium point of this system, no matter what x is, as long as you're not dividing by 0. As long as x is not -1, and as long as x is not -1/3, this will be a equilibrium point. So it consists of, it's really a curve. In fact, it's more than one curve. It's pieces of curves that are always equilibrium points for this system. And that, along with the fact that you've got invariant spheres, means you're going to have equilibrium points on any one of those invariant spheres. So let's look at the sphere, the flow on the sphere of radius 2. In lecture 36A, we looked at the flow on the sphere of radius 1 centered at the origin. Now let's look at radius 2. I hinted at a undergraduate research project you could consider to think about the bifurcation that happens as the sphere gets bigger. I hinted that you would get a bifurcation from 2 equilibrium points to 4. And in fact, when you look at the sphere of radius 2, you've got 4 equilibrium points on that sphere. This you can check with numerical approximations. that's going to be on the sphere of radius 2 when x is these 4 different values approximately. When you figure out the resulting equilibrium points by plugging those values of x into here, you get these 4 approximate equilibrium points in rectangular coordinates that are on the sphere of radius 2 approximately. These are not exactly on the sphere, but approximately. The flow, just like in the last lecture, is beautiful. Here it is. Looks fairly similar to the flow from lecture 36a. These 2 equilibrium points look very similar. We had those before, but these 2 are new. These 2 we had before when the sphere was smaller. The sphere was intersecting this orange curve here and here, just at 2 points. That's the curve of equilibrium, by the way. And so we had 2 equilibrium points in the sphere. But now that the sphere is bigger, we intersect the orange curve down here as well. We get 2 more equilibrium points. We've got some spiraling going on. This equilibrium point, and this equilibrium point all seem to be spirals. Are they spiral sinks or spiral sources? If I remember correctly, in the Mathematica, I see that this one ends up being a spiral source. The solution is to move away from it as time goes on. These 2 actually both end up being spiral sinks. Different solutions approach those 2 different equilibrium points depending on the initial conditions as time goes to infinity. And this point over here, you don't really see solutions approaching it either as t goes to plus infinity or minus infinity. That ends up being a certain kind of saddle point. So I am going to show you the Mathematica to try to see this, but I also want to show you that you can take this flow, these solutions on the sphere, and you can map it, project it, so to speak, to a plane. Really by considering what's called spherical coordinates, theta and phi. Now, I'm going to do something different than physics books do. I'm going to take theta to be the angle going around the sphere, and phi to be the angle going down from the top of the sphere, down from the North Pole. In physics books, they usually switch around the theta and the phi. They think of phi going around this way and theta going this way. But I'm more used to thinking of theta as the polar coordinate in the xy plane, and so I'm going to stick with that. This is a picture of that flow, actually also inverted because theta is an angle downward. Phi is an angle downward, excuse me. So theta equals 0 corresponds to this direction, the positive x-axis, where y is 0. And when you go around over to this negative x-axis direction, that's where theta goes up to pi radians, which would be 180 degrees. If I go backward the other way, theta goes backwards to negative pi radians, negative 180 degrees. So essentially we are seeing the entire flow in the sphere in this entire picture, because you can see theta is going from negative pi to positive pi. Phi is going from 0 to pi. Again, phi is 0, points straight upward, that's the North Pole. Phi is pi over 2, would be along the equator. Pi over 2 radians, which is 90 degrees. And when phi is pi, 180 degrees, you're down at the South Pole. Effectively, these 2 horizontal lines correspond to the North Pole down here and the South Pole up there. It's inverted. I didn't have to do it that way, but that's a standard thing to do with spherical coordinates. This, by the way, does correspond to the Mercator projection of the map of the Earth, this kind of thing, except inverted, okay? In this kind of picture, this entire line up here corresponds to the North Pole. This one down here corresponds to the South Pole. These 2 lines correspond to a line of what would be longitude, the same line that goes through like the tip of Russia up there, it looks like. Okay, so it is a very similar kind of thing. And we can now see the correspondence between these pictures here as well. And it's worth thinking about. And it can help you understand this picture because we could, for example, use linearization in the theta phi coordinates. We could figure out the differential equations in terms of theta and phi. I don't bother doing that, but we could do that. We could verify, for example, this one is a spiral source because this one corresponds to that point right there. These 2 things are spiral sinks. They correspond to these points over here and here. And this one right there, which you can kind of see better in this plane, corresponds to a saddle point. If we linearized at that point in this projection, we would get a Jacobian matrix that has real eigenvalues, 1 positive, 1 negative. That would be what we would see. Let's look at the Mathematica that animates this and helps us believe what I just said there. I've split this up pretty nicely. You can first enter the right-hand side functions in the vector field if you like. By the way, these as always are going to be in the course folder on the Google Drive. You can solve for the curve of equilibria. Here it is. You can plug it in as a parametric curve. Where does it intersect the sphere of radius 4? You can approximate where that is. Those are the 4 values of x where you get the intersection, and the corresponding points are these 4 points that you see here. Instead of null clines, when you're talking three-dimensional system, you have null surfaces. Surfaces where dx dt or dy dt or dz dt are 0. That's an interesting thing to think about. Here's what they look like in this case. So the red one, which is, if you can tell which one's red here, this one up here, is where dx dt is 0. That's where f is 0. The blue one, which looks like it's this piece, and are there any other pieces to it? Yeah, down here, that's where dy dt is 0. That's where g is 0. And the green one, that's where h is 0. That's where dz dt is 0. And where those intersect, that's the curve of equilibria. And they do happen to intersect along curves, not isolated points. Actually, usually when you've got 3 functions like this, f, g, and h, all equaling 0 simultaneously, they will usually intersect only at isolated points. So this is a very special system. And we get curve of equilibrium here. And we can figure out, well, how far they are from the origin if we like. I can use ND-solve to solve the system, and I can then look at the flow. Here's a picture of the flow. I can do an animation. That's what's going to help me see for sure which one's a spiral source and which 2 are spiral sinks. I'm letting t start at 0 here. I let it go a little higher. And I do see the red curve, for example, here spiraling away from this one. It looks like the cyan and green curves and maybe the magenta curve are going toward this point up there. We can step forward and see those go on. And it looks like all those curves except for the red one are spiraling up toward this one, but the red one's spiraling toward that one. Both of these points seem to be spiral sinks. And again, that point on the left is some sort of saddle point. So we can see that going on as time goes by. We can project the flow into the xy plane. This is not something that I've shown you yet. This is a straight projection onto the xy plane, and there's the finished product. I'll let you think about what that's doing. And finally, we can also project the system onto the spherical coordinates. That's the code that I have here. By the way, you don't have to fully understand this code. I was trying to avoid some asymptotes in what I was doing here. Here ultimately is the picture in spherical coordinates that I showed you, and then we can also animate it with the code down here. You don't have to completely understand this as long as you have Mathematica to do it. We encountered an error here. I'm not sure what's happening. It's saying something 0 over 0 is encountered. That did not actually happen on my computer, so I'm not quite sure what's happening here and why it didn't happen on my computer. But anyway, you can see the flow here. As time increases, you can see the one on the right there, well, if we get a picture at least, seems to be a spiral source. These curves are going away from it, and these 2 end up being spiral sinks here and here. Okay? Let's move on to the next example. A famous 3-dimensional nonlinear system called the Lorenz System, and its strange attractor called the Lorenz Attractor. What a strange sounding topic this is. This is actually very famous. This system was discovered by a person named Lorenz back in the 1960s, I believe. Who was Lorenz? He was a meteorologist. He was studying the weather and trying to approximate the weather with differential equations. The differential equations that people use to approximate the weather and the climate are very complicated, and so he was trying to come up with a simpler system that might still mimic the behavior of his more complicated system. And he came up with the following system. Okay, a pretty simple system, and in fact, there's only 2 nonlinearities, minus xz there and plus xy there. It seems like it's almost linear. How could this possibly have complicated-looking solutions? But the surprise was that it did, and the implications for the weather were very profound, and as well as other things besides the weather and predicting the weather. This system has equilibrium points at these 3 points. You can check it. It's not too hard to check. I would encourage you to do that. And you can linearize using the Jacobian matrix and the Hartman-Grobman theorem as we've talked about. So you find the 3 by 3 Jacobian matrix by taking partial derivatives of these things, plug in the equilibrium points. If you do the first one, the origin, it turns out to be a 3-dimensional saddle point with real eigenvalues two of which are positive, negative, excuse me, giving something called a two-dimensional stable manifold, solutions going toward it, and one of which is positive, giving what's called a one-dimensional unstable manifold, a curve of solutions go away from it. However, when you are near that point, in spite of the fact that the stable manifold is two-dimensional, an arbitrary initial condition near the point will go away from it because of the saddle point kind of nature from it. The other 2 points, this one and this one, turn out to have two-dimensional unstable manifolds that include spiraling, so there are two complex number eigenvalues that are non-real, that also have positive real part, that's why it's unstable, it's a source in that direction, and a one-dimensional stable manifold. They each have this kind of behavior. You can check that out. However, even though this nonlinear system seems fairly simple, its solutions are chaotic. What does that mean? I'm not going to give you a full definition of chaos. You can give a full mathematical, rigorous definition of chaos. Chaos that's very precise. I'm just trying to get the basic idea across. Basically mean the fine behavior of solutions, meaning their actual values and the actual nature of the graph to the precise kinds of details that we are usually after, is actually quite unpredictable in the long run. In the short run, it's fairly predictable, but in the long run, it's quite unpredictable. And they display what's called sensitive dependence on initial conditions. This is a very profound thing. What it says is arbitrarily small changes to your initial condition drastically affect the long-term behavior, make it completely different in the long run. In the short run, it's basically the same, but in the long run, it can be different. This is the so-called butterfly effect. Again, arbitrarily tiny changes. Arbitrarily tiny changes, no matter how small, in fact, lead to drastically different long-term output values in their fine behavior. Now, their rough behavior, in terms of the basic patterns, end up being similar, but the fine behavior, like trying to predict what the high temperature is going to be, say, 2 weeks from now, well, changing the initial conditions slightly can definitely affect the long-term behavior. And that's the butterfly effect, which says, say a butterfly is sitting on a branch on a tree, and in its little butterfly mind, it's trying to think to itself, should I take off or not? And the moral of the story is if the butterfly does not take off, then 2 weeks later it's sunny. If the butterfly does take off, changing the initial conditions ever so slightly, then 2 weeks later it's rainy. Can that really happen? The idea of chaos in the butterfly effect, sensitive dependence on initial conditions, is yes, it can happen. Can you really prove it can happen? Well, mathematically you can prove it can happen. Does that happen in reality? There could be complicated factors that maybe don't change the weather in 2 weeks based on the butterfly in reality. Maybe there's some damping effects in real life. But the theory, the mathematical theory, says that it can happen. I mean, you can even go so extreme as saying there's a tiny little pebble on a hill on Mars, and it's about to roll down the hill or not. If it does roll down the hill, that affects the weather in one way, and if it doesn't, it affects the weather in another way. Here on Earth, say, I don't know, 2 months later. Okay, you can even go so far as saying, because that affects the gravitational pull of Mars on the Earth and vice versa, you can even go so far as saying that because these tiny changes are arbitrarily tiny, that's why you can theoretically say it. Here's a picture of the Lorenz Attractor. Isn't it pretty? Of course, there's a picture on that first slide that I showed you. But now I added a bunch of different solution curves and colored them differently. Very pretty attractor. Even though the fine behavior of the solutions is unpredictable, we'll see it in Mathematica here in a second, there's still a rough predictable structure to the solution curves. They all approach this kind of picture. No matter what initial conditions you pick, in the long run you get this kind of picture. That's the rough structure. This is called a strange attractor, which in this case is called the Lorenz attractor, because Lorenz was the person who discovered it. All right, so let's look at the Mathematica for this. We'll also look at the Kinney Attractor. So let's see here. Here are the right-hand side functions in the vector field for the Lorenz Attractor. It's got isolated equilibrium points. We can plug those in there. We can look at the null surfaces again. They intersect at just those 3 black dots that you see there. Not along a curve. You can do the Jacobian matrix. You can compute the eigenvalues of the Jacobian at the equilibrium points. This is the eigenvalues for 0, 0, 0. You can see 2 negative and 1 positive. Here are the eigenvalues for the other ones, 2 of which are complex numbers with positive real part. You can compute the eigenvectors if you want. I'll let you think about what that would imply. You can approximate solutions with MD solve. You can look at the flow. And let's go ahead and just animate the flow and see how a solution, well, initially seems to head toward that equilibrium point that you see there. But then it's an unstable equilibrium point, so it goes away, and it eventually heads toward the other equilibrium point, but then comes back to the other one. The first one then goes back to the one on the right, then the one on the left. It goes back and forth in a seemingly arbitrary kind of way. Pretty amazing. We can also look at the graph, for example, of x versus time and see it behave in a chaotic way as time increases. Yeah, especially once we get past time equals about 17 or so, it's behaving chaotically, kind of unpredictably. And yes, if you change the initial value of x, say, ever so slightly, from 1 to, oh, I don't know, 1.0001, watch it here, I'm about to enter it. Initially, it'll seem very similar. This part of the graph will seem very similar, but over here it'll change completely, although it'll still have a similar up-down pattern. Ready? 1, 2, 3, go! Yeah, it changed. Initially, it's the same over here, and over there it changed. That's sensitive dependence on initial conditions, and it doesn't matter how close an x0 to 1, as long as I make it slightly different from 1, that kind of thing will happen. Pretty amazing. It also tells you maybe your numerical methods, maybe even ND solve and Mathematica is not completely telling you accurately what's happening, because there's always numerical errors. That's another implication of it. What's the Kinney Attractor? It's a system that corresponds to these right-hand side functions, and I made it as part of my thesis, and it's just kind of a pretty picture. There is the Kinney Attractor. There are some chaotic aspects to this, and here is x, y, and z as functions of time for the Kinney Attractor. This is what's called a fast-slow system. The oscillations happen very rapidly. There's some rapid oscillations right there. And then all of a sudden, there's no oscillations, and it changes very rapidly, and then comes back to oscillating again. Pretty interesting behavior, I think, in that fast-slow attractor, the Kinney Attractor. And yes, you can play with the Kinney Attractor if you like, if you want to download this Mathematica notebook. All right. A couple more subjects for this lecture. Again, trying to get a big overview of things. Let's talk about the two-body problem. It's a four-dimensional first-order system, actually. We can first think of it as a two-dimensional second-order system. And we can visualize it in a two-dimensional physical space instead of a phase space. I'll talk about the distinctions between those as we go here. Consider two masses, capital M and little m. I am abusing notation here and letting capital M and little m be both the labels for the masses and their numerical values for those masses. So capital M is the big mass, like the sun, say, and little m is a little mass, like the Earth, relative to the sun, though the Earth does exert a slight gravitational pull on the sun. If we want to get more extreme, we could pretend it's a rock flying around down in space, okay, or a comet or something like that. We're going to pretend the big mass is so big compared to the little mass that the big mass will stay fixed where it is. And the little mass is affected by the gravity of the big mass. The idea is the little mass is going to revolve around the big mass because of gravitation. Now, I'm not going to get into a ton of details about the nature of gravity, but we'll try to get the basic idea here. Yeah, suppose capital M is so large compared to little m that only little m is affected by the gravitational pull of big M. Capital M is going to stay fixed where it is, and might as well take that to be the origin. We're going to let R be xy transpose, a vector that technically I would want to think of as a column vector. That's why I'm putting the transpose there. Don't have to think of it that way, but it's sort of best for us. Be the position vector of the mass, little m, a function of little t, time. That's implicit. Let v be its derivative, be the velocity vector of that mass. Inappropriate, non-standard, non-SI units. Newton's second law and Newton's law of universal gravitation, the inverse square law, imply that this differential equation would hold for the motion of the little mass, little m. M times the second derivative of the position vector with respect to time, which is the same as m times the first derivative of the velocity vector, is m times the acceleration vector by definition. That's not no physics going on there besides just what position, velocity, and acceleration are. The physics is this equality right there. This thing right here is the nature of the gravitational force. Now, in real life, when they apply this to real situations like the Earth going around the sun, there's an extra constant of proportionality in here called capital G, the universal gravitation constant, which in standard units has a very small value in standard units. But to simplify things, I'm taking G to be 1 in non-standard units. And I'm also taking capital M to be 1 in non-standard units, which would mean little m would be, microscopic or something. The little m is going to cancel on both sides of this differential equation. It's going to go away. Only capital M matters. What else is going on here? You should realize that this quantity right there that I've just put parentheses around is a scalar quantity. Negative capital M over the length of the position vector squared. That is a scalar quantity. We don't want to divide by 0, so we're not at the origin. The little mass better not be at the origin, otherwise it'd be inside the sun anyway. And you're multiplying the scalar by a vector quantity, the position vector divided by its length, which is a unit vector. This is a unit vector. The magnitude of the force is the magnitude of just this part, because that's a unit vector. And it's called an inverse square law because you get the length of r squared in the bottom of it. However, when you write it as a vector equation, you need the negative sign here because the force has to point from the little mass toward the big mass. That's got to be the direction of the force. The position, if this is at the origin, the position vector is like this. That's r itself. But the force vector has to point in the opposite direction, and in fact toward the origin. That's why we need the negative sign there. You can simplify it if you take capital M to be 1 to this. And if you do so, because we've got the length of r squared times the length of r down in the bottom, it actually becomes the length of r cubed in the bottom. But it's still an inverse square law because of the square there, and because this is a unit vector. So don't get confused by that. Of course, we know the magnitude of a vector is the square root of the dot product of the vector with itself, so the magnitude of a vector cubed is r dot r to the 3/2 power. And this is our differential equation as a vector, single vector equation that's second order when r is non-zero. Okay? As a second order system, it's two-dimensional. If I think in terms of the components of r, x and y, I get this system of two second order equations in terms of those scalar quantities, little x and little y. If I bring the velocities in both the x and y direction into play, then I get a four-dimensional first order system. Here it is. dx dt is vx, that's the component of the velocity in the x direction, by definition. dy dt is v sub y, that's the component of the velocity in the y direction, by definition. And the derivatives of those velocity components I get from these equations up here. We now have a four-dimensional first-order system with a four-dimensional phase space, though it's not all of R4, because you'd want to avoid dividing by 0, you would want to avoid the subspace. Well, maybe we shouldn't call it a subspace. The set of points in four-dimensional space where x and y are both 0. You'd want to avoid that. However, we can still visualize solutions, even though you can't visualize 4 dimensions, in 2 dimensions, in a physical space, because we can actually look at the orbit of the mass, where you see x and y changing over time, like I'm hinting at with this picture here. And you can also see even the velocities changing over time if you draw the velocity vector in the picture, which is what I'm going to do. Visualize them in the standard ways. We'll look at Mathematica here in a minute. In physical space, we get this kind of picture. We see x and y. And we also see, well, the blue vector is the position vector. The red vector is the velocity vector. I made a big yellow dot for mass capital M. That's the sun. I made it yellow, yay. And blue, I guess that's the Earth. That's the little mass. Made it blue. Of course, this orbit you can see is not circular. It's pretty strongly elliptical, much more strongly than the actual Earth's orbit. So maybe it'd be better to think of this as a comet. It can get even more extreme as well. And as you let time go by, if you graph x and y as functions of t, the parametric curve, you get this kind of graph. I will show it to you in Mathematica. And it does obey Kepler's laws. Now, many people don't know the details of Kepler's laws, but one of Kepler's laws says that the orbit of a planet or an asteroid or a comet around the sun is in general elliptical. Even for the Earth, it's slightly elliptical. That's one of Kepler's laws. Another of Kepler's laws says the position vector here, the blue vector, sweeps out equal areas in equal times. What that means is when the blue mass here is closer to the big mass, the yellow one here, the sun, it's got to move faster than when it's further away, if it's going to sweep out an equal area in an equal amount of time. So comets especially, it's pronounced, when they go close to the sun, they move pretty rapidly. When they get further away, they slow down. We're going to see that in the Mathematica animation. Can we also visualize it some other way? Yeah, you can project from the phase space. You can, for example, ignore one of the coordinates. Here in this picture, the xy plane, is this plane here. X is this direction, y is that direction. And v sub x, the velocity in the x direction, goes up and down. I'm just ignoring v sub y. And I get this picture, which is in 3 dimensions, which we'll see in Mathematica as well. I didn't have to ignore v sub y. I could have ignored one of the other variables, but let's just go ahead and see what this looks like. Got the vector field, got to enter this. There are no equilibrium points, by the way. The solution set where all these equal 0 is empty. That should make physical sense. You're never going to have a gravitational situation where an object doesn't move, and also, where x and y stay constant, and also the velocities are 0, say. That won't happen. You can use empty solve. You can look at the solutions represented in physical space. And we'll watch this here as time goes by. And I need to make the orbit more elliptical here by changing the initial conditions a little bit, say. We're going to see Kepler's law, in particular his second law, that it moves faster when it's closer to the sun and slower when it's further away. In play here, the red arrow, the velocity vector, is longer on the right side of the picture and shorter on the left side of the picture. It's moving faster when you're on the right, when you're close to the sun, and slower when you're on the left, when you're further away from the sun. And I can change the other initial conditions if I want as well. I can make the ellipse be rotated to some degree. That can happen as well. I can also change my viewing window here. So kind of a fun thing to play with there. Remember, these are non-standard units, so it's not actually modeling what's going on with actual planets, though you could adjust things to make it do that. And here we're seeing the projection onto x, y, vx space, and I can rotate this picture. And I can now, for example, see that when time is just barely positive, x became, it gets smaller, we can see vx becomes negative here, meaning x is decreasing at that point. But then eventually, when you get back to the other side, vx becomes positive, so x starts increasing, and you can see how this gets affected by changes in the initial conditions as well. If I change x0, it gets elongated in strange looking ways, but still is giving you an accurate representation of x, y, and the x component of velocity as functions of time. Okay? All right, the final thing to show you here is the double pendulum. Here are the equations. Okay, I'm not deriving these equations. They're super complicated, but we can visualize the unique solution of this particular initial value problem in Mathematica. We can look at an animation in physical space if we like. Double pendulum, very nice animation to think about here, very fun to look at and wonder exactly what's going on and wonder if it's really accurate or not. Of course, there's actually no friction in this particular example to To make it more realistic, we'd have to add friction. We can look at projections of this in physical space as well, or excuse me, of phase space, and it's pretty interesting. You get lots of strange looking squiggles. And it'd be interesting if you got Mathematica to take the time to compare the solutions you're seeing as the projections from the phase space and how they compare to the actual motion. Alpha and beta are the two different angles, and in that picture we are seeing also alpha prime and the rate of change of the alpha angle versus time. I believe the alpha angle is for the black pendulum, and the beta angles for the red one. Okay? So that's the last thing I wanted to show you here in Lecture A. I hope it was inspiring. Thanks for watching.